We are going to learn about the major enzymes used in the food industry. Enzymes can modify and improve the functional, nutritional, and sensory properties of ingredients and products, and therefore enzymes have found widespread applications in processing and production of all kinds of food products. Their uses include the production of food ingredients and commodities such as high fructose corn syrup, glucose syrup, another example, protein hydrolysate, they are used in structured lipids, and different application like wine clarification, meat tenderization, so even in dough mixing they have major roles. So it goes like that. There are many examples and applications. Let's see the major ones. Remember, enzymes are grouped into 6 major classes from AC1 to AC6. It's on the basis of the reaction which they catalyze. So oxidoreductases catalyze oxidation and or reduction reactions. The examples for enzymes in this class are glucose oxidase, catalase, peroxidase, polyphenol oxidase, or lipoxygenase. Glucose oxidase has broader applications for the food processing industry. So this enzyme is produced by fungi Aspergillus niger and Penicillium notatum. It catalyzes glucose oxidation by consuming oxygen from the air, the molecular oxygen. So we have a glucose here, it's in beta form, beta D glucose, and the other reactant is oxygen. We have glucose oxidase enzyme, and here glucose is oxidized to D-gluconic acid. We oxidized glucose and oxygen is used. We removed oxygen from the environment. So that's why it's used for removal of either glucose or oxygen. So what else do we see here in this chemical reaction? So H2O2, what's that? It's called hydrogen peroxide. So it's the byproduct of this treatment. So this byproduct, hydrogen peroxide, can be used in other specific applications such as canning, pasteurization, for example, pasteurization of milk with hydrogen peroxide. It's an alternative to a thermal process. Or it can be removed from the environment. For this purpose, catalase enzyme is used. Actually, it's coupled. Glucose oxidase is coupled with catalase. So here, catalase, another oxidoreductase enzyme. So if we do that, catalase enzyme decomposes hydrogen peroxide into water and oxygen. and hydrogen peroxide is eliminated, removed from the environment. Let's see the applications of glucose oxidase in food industry. It is used to remove glucose during the production of egg powder, egg white powder. By removal of glucose, formation of Maillard reaction is prevented, which is responsible for discoloration of the product. Similar use of glucose oxidase for some meat and protein products would enhance the golden yellow color rather than brown color of potato chips or French fries, which is obtained in the presence of excess glucose. It can be used to remove oxygen. The shelf life of juices, beer and wine can be prolonged with this enzyme since the oxidative reactions which lead to aroma deterioration are inhibited. So another example is the color change of crabs and shrimp from pink to yellow is inhibited by dipping them into a glucose oxidase catalyzed solution. So in food industry, it's mainly used to preserve aroma and color of the food products. Another individual enzyme in this group is lipoxygenase enzyme. So lipoxygenase catalyzes the formation of lipid peroxides, as you remember. The formation of lipid peroxide from polyunsaturated fatty acids. Lipid peroxides are crucial in the oxidation of fats to form rancid flavors. And peroxide activity can quickly lead to off flavors, destruction of essential fatty acids. So that's why it's undesirable. So it can cause deterioration of color, aroma and taste during storage and processing of oils and oily foods. Soybean and other oilseeds and some grains have lipoxygenase, which causes rancidity. It contains non-heme iron and it's activated when ferrous iron is converted to ferric iron. So it can be inactivated by using a heat treatment, such as thermal blanching. So how can we use this enzyme in food industry for a desirable result? It's widely used to bleach wheat flour. So generally, soy flour is added to bread dough to bleach the dough because soybean has lipoxygenase. So how it works? The radicals, the breakdown radicals can co-oxidize pigments. So they are bleached. Let's continue. So another oxidoreductase enzyme commonly used in food industry is polyphenol oxidase, PPO. It's present in plant tissues and some seafood. This enzyme catalyzes the oxidation of a wide range of phenolic compounds. phenolic compounds, phenolics. So that's the oxidation pathway. So these phenolics are oxidized to monophenol, diphenol, and quinones. So then these quinones here spontaneously polymerize to brown melanin pigments. So it's a spontaneous reaction. It occurs non-enzymatically. So polyphenol oxidase only catalyzes oxidation of phenolics. And the end product is quinones, and then these quinones spontaneously turn into melanins, brown pigments. So polyphenol oxidase is not acting on quinones, only oxidize the phenolics. Okay. And for its activity, polyphenol oxidase needs oxygen and copper. So what is the function of copper? Here you will remember from the previous lecture, it's cofactor. So this polyphenol oxidase is a holoenzyme, and it needs copper as a cofactor for its activity. So we said this enzyme is found in plants. Normally, this enzyme's activity is a plant defense mechanism designed to turn natural plant phenols into antimicrobial products in the case of tissue injury. Okay, let's continue. This formation of this brown pigment, melanins, can be desirable in prune juice, coffee, cocoa, apple cider, and tea. Optimum pH for this enzyme is between 4 to 7. And optimum temperature is between 30 to 50 degrees Celsius. So how can we inhibit this enzyme if we don't want the formation of melanins, the brown pigments? So we said this is the optimum pH. So that's why one inhibition strategy can be acidification. So when we decrease the pH like below 4, when we acidify the medium, we will decrease the activity of enzyme. For example, when we dip the apple slices in citric acid solution, we can prevent the formation of that brown color. So another way can be heating above 50 degrees Celsius or blanching for a few minutes. Or chelators can be added. Such as citric acid. So you are going to remember these chelators from minerals chapters. So it's used to bind copper. So we said that copper is the cofactor of the polyphenol oxidase enzyme. So if we bind the copper, so this enzyme will lose its activity. Okay, let's continue. So EC3 hydrolases. Most of the enzymes used in the food industry belong to the class of hydrolase enzymes. They catalyze the hydrolysis of chemical bonds, hydrolytic splitting of substrates. It occurs based on the type of bond hydrolyzed. So we have different enzymes in this group based on the hydrolysis of peptide bonds, ester bonds, or glycosidic bonds. So proteases are enzymes which catalyze the hydrolysis of peptide bonds present in proteins or polypeptides. These peptide bonds between amino acids. So it's called proteolytic action. They present 60% of industrial enzymes on the market. Proteases can be classified based on their origin, catalytic activity, and nature of the reactive group in the catalytic site. The major sources of protease enzymes are animals, plants, and microorganisms. They are divided into two groups: endoproteases, exoproteases. So it's based on the site of action on polypeptide chains. The exoproteases act on the ends of polypeptide chains. And endoproteases act randomly in the inner regions. It can be in the middle. And these two groups can be further classified into different groups. But it's based on the catalytic residue present in the active site, such as it can be serine protease, trypsin, pepsin, renin, or according to end site, like carboxypeptidase, aminopeptidase. It's carboxy if it acts on the carboxyl site, or amino if it acts on the amino end. So like this. Proteases such as bromelain, papain, renin. So these are widely used in food industry for various applications such as brewing, tenderization of meat, coagulation of milk, or as a digestive aid. Renin. Renin is widely used in dairy industry. It's also called chymosin. So it's an acid protease. That means it shows optimum activity at acidic pH condition. So it's a gastric enzyme with high milk clotting activity. So it hydrolyzes a specific peptide linkage between these two amino acids, phenylalanine and methionine, in casein protein, paracasein, kappa casein. So it destabilizes the colloidal structure of casein and hence act as a coagulant for cheese curd formation. So rennin is used in cheese making. Making cheese involves many steps, but essentially it's simply the process of turning a liquid into a solid. So we start with the raw milk. Milk contains about 86% of water, but also contains fat, carbohydrate, mainly lactose, proteins, minerals and vitamins. What kind of proteins? Casein and whey proteins. So cheese making is the controlled process of removing water from milk. So it involves coagulating of the casein protein in milk and then separating the milk into solid curds and liquid whey. We have solid curds and we drain the liquid whey. Okay, the liquid whey is drained away. The curds are salted, shaped, and left to ripen in a controlled environment, depending on the cheese type. Here, rennet plays important role in coagulation. So rennet is a mixture containing the active enzyme rennin. So it causes coagulation of casein and produces a strong curd. Breaks down the kappa casein. On the surface of the micelle. So you know, milk is an emulsion of fat globules and a suspension of casein micelles. So this breaks down, change this from being hydrophilic to hydrophobic. Then this causes them to aggregate together, trapping fat and water molecules in the developing curd. So curd, which is basically the cheese. So it just needs some time ripening to develop the desired aroma and flavor. Papain is a cysteine protease enzyme. It's present in papaya fruit. It has a high optimal temperature and it's active over a broad range of pH levels. Its maximum activity appears to be in the range of 5 to 8. So this enzyme contains thiol group. As active site. So oxidation of this active site can lead to inactivation of the papain. Papain is often used as a meat tenderizer. Toughness of meat is generally due to the presence of collagen, elastin, and also actomyosin. So papain can hydrolyze the peptide bonds of collagen, elastin, and actomyosin and tenderize the meat. So another cysteine protease is bromelain. So bromelain is a plant protease isolated from pineapple, from all parts, juice, peel, and stem. So it's from papain family, and it cleaves specific peptide bonds. So this enzyme has strong hydrolytic activity, and it created a wide interest in numerous applications, mainly in tenderization, meat tenderization, brewing, baking industry, beer clarification, and many other applications. So it's inactivated during pasteurization, and this thermal denaturation is irreversible. So since this is the case, for example, if you wanna marinate your meat, you can use fresh pineapple juice. It will tenderize your meat. But if you have a canned pineapple juice, the result won't be good because it's canned, and during canning there's a pasteurization process, and this will destroy the enzyme activity in canned pineapple juice. So you cannot marinate your meat with canned pineapple juice because of the thermal denaturation of your enzyme. Another hydrolytic enzyme group is glucosylases. So in this group we have amylases and pectic enzymes. As the name relates, amylases, they work on amylose and amylopectin. They are called starch degrading enzymes. And we have pectic enzymes. They work on pectin. So they hydrolyze glycosidic bonds. Alpha and beta amylase enzymes. These starch degrading enzymes capable of hydrolyzing alpha-1 for glycosidic bonds of polysaccharides. So different reducing groups are released and different products are formed. They are used to produce some oligosaccharides, maltodextrin, maltose, glucose, or only maltose. We also have glucoamylase enzyme. It hydrolyzes alpha-1, 4 and 1, 6 linkages and produces glucose. So it removes glucose in a consecutive manner from the non-reducing end of the substrate chain. In starch industry, these amylases find application for starch liquefaction, which converts starch into glucose and fructose syrups. So this is an illustration for a starch saccharification process. The action of amylases yield starch syrup, which is a mixture of glucose, maltose, and dextrins. So different end products can be obtained by using different enzymes or enzyme mixtures. Amylases are also used in baked goods. So they are added to bread formulations to provide substrate for yeast. So they are added to decrease viscosity of the dough. And they also have a function, decrease staling of the bread. So invertase is another enzyme group. So by using an invertase enzyme, we can convert sucrose to glucose and fructose sugars. So invertase gets its name because it inverts the rotation of light when a solution is shown through plain polarized light, as you will remember from the carbohydrate chapter. So invertase enzyme is generally used in soft centered candies like this. So why invert sugar is wanted? Because invert sugar is sweeter, it will be less prone to crystallization, and also has lower water activity at the same concentration. Okay, let's continue. So other glycosylase enzyme is pectin esterase. So pectin esterase catalyzes the deesterification of pectin into pectate and methanol or pectic acid. So they hydrolyze the methoxyl group of pectin. So it's the ester linkage. Methanol and galacturonic acid. So this is one of the most heat resistant enzymes. So it leads to gelation and precipitation of pectin in puree and juice with subsequent loss of cloudiness. And the last group is lipases. So lipases are enzymes which catalyze the hydrolysis of long-chain triglycerides. They are naturally present in the stomach and pancreas of humans and other animal species in order to digest lipids. Microbial lipases are produced by bacteria, fungi, and yeasts. Commercial lipases are mainly used for flavor development in dairy products and processing of other food-containing fat. They can improve the characteristic flavor of cheese by acting on the milk fats to produce free fatty acids after hydrolysis. Limited hydrolysis of milk fat is desirable. It can be of interest in the production of chocolate milk because it enhances the milk character of the flavor. Lipase catalyzers could improve the texture and softness of cheese. They are also used as flavor development agents in butter and margarines. Staling of bakery products is retarded by lipase. It's due to the release of mono and diglycerides. And in gelatin production, it facilitates the defatting of bones. So there are various applications of lipases in food industry. Okay, that's all for this lecture. Let me know if you have any questions.